So we learned about GNNs, specifically the common message passing GNNs. And we also looked at the heterogeneous versions of MPNNs, um, the definition, the different variations, and so on. So we know how they look like. In the third part, we're going to talk about some pragmatic aspects that take place once we are using the GNNs and specifically learning them. And some of these pragmatic aspects are just, carried over from the fact that we are applying deep learning, and some are actually specialized to graphs, okay, to GNNs. Okay, let's start with learning anomalies or training anomalies. Okay, so the issues that we are encountering generally in deep learning, vanishing gradients, exploding gradients, they still hold, and we still need to deal with these in the usual ways, skip connections and normalization and so on. Okay, but there are also some graph-specific challenges that I want to highlight. Okay, and these are known and common. One is called oversmoothing, and it is due to the fact that we are basically aggregating a lot of information in our JNN functions. Okay, and basically, when we do that, disaggregation in several layers, the the nodes tend to see kind of this similar input. Okay, it's difficult to distinguish between the different inputs, so they become too similar. Too similar, meaning that we do not really distinguish between different cases, between the more nuanced differences, and therefore we lose accuracy. Okay? And ways of dealing with these are similar to what we are doing with vanishing with the exploding gradients, specifically with vanishing gradients, which are using skip connections, okay, connecting the input directly to the output of the layer without going through the constructs in between, like the attention and normalization, where we basically bringing the full layer into some normal distribution, okay, like mean of one, standard variation of one and mean of zero, okay. Another problem is over squashing. And this is specifically referring to the case where um, we, ideally would like the nodes to be able to incorporate, okay, or the function that we apply to the nodes to be able to incorporate information from distant nodes, so that when you have some nodes that are farther, not direct neighbors, but maybe more distant, we would like them to impact the decision. We would like the decision of the that is applied to the node, or the value, the embedding that we are associating to the node, to be a reflection of the close, the nearby values, and also the further values, okay, or the further patterns. However, because we are going through um, several distances, basically several rounds, in order to incorporate the information in the node, and each includes its aggregation, these long distance impacts are essentially diminished. Okay, and we say that they are squashed. These impacts are squashed through the layers. And ways of fixing that or dealing with that can be um, graph rewiring. Basically, when we uh, take long distance paths and create a shortcut of edges, thereby making important nodes closer to the nodes of focus. Okay, so this is called the graph rewiring. And another thing is using attention mechanisms that essentially allows the node to focus on what is important. If that information tends to be distant, then so be it. Okay, so I'm really describing it generally, not getting to the details of these anomalies. I just want you to be aware of these. Okay, so these are two figures that illustrate what is going on. So here we have two data sets, okay, publication data sets. And so each row is a data set, and each step in the or each chart in each row from left to right shows what happens when you're doing more steps, more message passing around. Okay, so you see that we're starting here with high variation, the points are scattered, and then more steps, they become more condensed until when we are making more and more steps, they actually are condensed into this um, very small region. So they become very similar. And this is reflected in the error. Okay, you can see that we are maybe underfitting in the beginning. Then at some point, we have a proper distribution, so the error is reduced. And then at some point, when they become similar, when they are over smoothed, you see that the error actually arises or rises. Okay. And this one is an illustration of a squashing. This is due to work that was done at the Technion, um, where basically you can see that the information that you have from these long distance nodes uh, flows into our target node. And you see that we have here this bottleneck. So a change, in this further node, okay, this change may be actually quite significant for our task. But this change is essentially diminished, squashed by going through more nodes, creating bottlenecks, and as it says, squashing all of the information into these bottlenecks until in the end we are reaching the target node.